Okay. So where are we? We're talking about exponential models still. It's a big topic. And the last thing we did was show the duality of the maximum likelihood principle applied to exponential models with the maximum entropy principle applied to satisfying constraints. Right? So that's an important sort of result, an important way of looking at it. So I'd like to review it. Wow. Okay. Max-Ent modeling says choose aspects of the data to model, aspects of the problem to be modeled, express them in a set of features, of feature functions. So far, the features that I gave you were dependent on the history and the word, because the model that I was discussing was a conditional model. So the feature would depend on both the conditioning part and what is being predicted. But that's not essential. You can also use everything we said about exponential models and about conditional models to model non-conditional distributions. And in a sense, that's simpler. So let's, for a change, have the discussion today in terms of non-conditional models. So the feature is of the input, which is some x, any kind of input. So we're trying to build a density estimator for x. Maximum modeling of P of x. So choose some aspects of x to be modeled, whichever aspects you believe are important. And then express these aspects in a set of features, feature functions. And then require that the solution, that the model satisfy some linear constraints over the FIs. Meaning the expectation according to the model of the FI is some fixed value. Expectation according to the model means a sum or integral over all possible values of x. This means integral, say, over dx of fi of x weighted by the probability that the model assigns to x. And this is some number. Or if x is discrete, it will be a sum. So set conditions on the expectations of the features. And this, to satisfy all the i's, the set of P's that satisfy all of this is either empty, namely the feature functions with their constraints are inconsistent. There's no probability distribution that satisfies all of them. Could be empty. Could be empty. In which case you're screwed. Otherwise, choose the one among them, among the set. So the set S, choose the one among S with highest entropy. In a formula, it would be P maximum entropy of X is the argmax over all P's of X, all possible functions in the universe over X, such that E under P of Fi equals Ki. So you maximize over all the things that satisfy this for every I. What do you maximize? You maximize H of P of X. We all know what H of P of X is, right? It's sum of pi log pi over all possible x's, or integral if x is continuous. This is the maximum entropy principle. There's one situation where we know the constraints are not inconsistent. We know they are consistent. And that is when the Ki, I mean, there may be other situations, but one important situation is when the Ki is equal to the empirical distribution of the Fi. The empirical distribution in some training data. If there's one fixed set of training data, and you derive Ki from that training data, that particular p-twiddle empirical distribution, then we know that the training data, the empirical distribution of training data, is one member of the set. Not necessarily the highest entropy member. In fact, chances are it's not. Chances are it has low entropy because it's not smooth. How is this defined? This is simply 1 over n, sum over the training data of Fi of x. X goes from the training data. So you just count over all your training data how often Fi was on, or if Fi is multi-valued, this works too. So this is how you do Maxent modeling. This is how you define it. It does not give you a constructive way of coming up with a model. It just gives you a principle for how to choose a model. The dual problem is the maximum likelihood over exponential. There's nothing here that mentions exponential family, by the way. There's no guarantee a priori that the set S of all the functions, all the distributions that satisfy the constraints is or is not a member of the exponential family. In fact, we do know that there's one member of the exponential family that is in that set, but that comes later. Yes.
I actually have a question about the Maxent model. So you said that it can be empty sometimes, so that's in the case where there's no empirical data, there's no training data?
It's in the case when the constraints over the features cannot all be satisfied at the same time. So an example would be, let's say, two features that are actually the same feature, and one of them is forced to have an expectation of 3, and the other one is forced to have an expectation of 5. That can't be if it's the same feature. Let's say a more likely scenario, one feature is a linear combination of the other features. Then its expectation must be the same linear combination of the expectation of the other features. But if you insist on it being something else, it cannot be satisfied.
Well,
Yes.
so those constraints are not derived from any empirical data?
They don't have to be.
Okay.
For the general framework of maximum entropy, the definition is you define features over your space of possible data. Features are computable functions of your input of the data. You define some features that you care about. You define some k target values, ki, and you say, I want to find the highest entropy model that is within the set of models that satisfy all of these constraints. The ki, the target values, do not need to be derived from any particular training data. If they're derived out of thin air, then you don't have training data. That's fine. In a real world, in practice, often you have training data and the target values are derived from the training data. But it is not, mathematically speaking, part of the definition of maxent model. It is part of the definition of maximum likelihood over exponential family. When you talk about maximum likelihood, it's maximum likelihood of some training data. So now let's talk about the maximum likelihood framework. Maximum likelihood over exponential family. You start from the same starting point. Choose features, feature functions, fi of x. I goes from 1 to n. And now you define a family which is defined in terms of these features, but with the parameters not specified. So the family is p of x equals 1 over z e to the power of sum of lambda I delta fi of x. I goes from 1 to n. Notice now that z in the conditional formulation was a function of h, of the conditioning event. So it would have a different value, different normalizing value for different h. Here, there's no h. This is not a conditional distribution we're after. It's a regular distribution. So z is a single constant, single number. And these are the parameters. And as you vary the parameters, you get a different member of the family. So you define that family and you say, I want to live in this family. And now, how am I going to find a particular member of this family that I want? Well, I'm going to take some training data, and I'm going to maximize its likelihood. So the next step here is get some training data. And the step after that is the lambda maximum likelihood, the maximum likelihood choice, and you may choose to stay within the exponential family and not look for the maximum likelihood solution. For example, we talked briefly about a map solution that starts with some prior over the lambdas. That will be fine too. The map solution is the one that maximizes over all possible lambdas the probability of your data given the parameters. And in this case, we have a constructive method for finding these values. It starts with the observation that the likelihood function is convex in the lambdas. So searching that space is not going to be hard. And there is a guaranteed unique maximum. You're not going to get stuck at the local maximum. And what you use, you can use actually different things. The algorithm we discussed is called generalized iterative scaling. There's another version of this that is, under some conditions, faster. It's called improved iterative scaling. And you can use other methods as well. You can even use gradient descent. So you'll need to calculate the gradient and take a step. Gradient with regard to each lambda, take a step. When things are convex, there are many ways of solving them.
Given that these two problems are the dual of each other, which one is easier to optimize for?
Well, definitely this one. Because I'm giving you here an algorithm, and I'm mentioning there are several others that will find the solution. Here, I didn't give you a method of finding it. I don't even know how to enumerate the set S of all distributions that are consistent with all my constraints. But one way of solving this is to show mathematically that it's the dual of this. Basically use the Lagrange multipliers, and then it becomes this problem.
Okay. But the set S, does it contain functions which do not belong to the exponential family?
Absolutely.
Okay.
All of them do not belong except for one.
Just one, and that
Right.
is the one which is the maximum.
Exactly. And the other way around too. So if you remember the picture from last time, we'll keep this down here. We had the exponential family here. Was this the exponential one? I think so. Yeah?
Yeah.
Vertical one, exponential. So this is the exponential family. With the specific features f1 through fn. As you move up and down this line, which is not really a line, it's actually belongs to r to the power of n. So this is because every lambda is free to be any real number, and they're independent of each other. So any point in n-dimensional Cartesian space represents a particular member of this set, right? As you move up and down, you're changing. It's not up and down. It's an abstract up and down. But as you move in this set, in any one of the n directions, you're changing the values of the lambdas. And now is another set. This is the set of all p's such that for every I, E under P of Fi equals E twiddle Fi. Namely, all the probability distributions that satisfy all the constraints. Again, it's not a line, it's a high-dimensional space. It is a convex set, right? Because if you take two distributions, P1 and P2, that satisfy whose expectation, if E according to P1 of some F17 equals what we want it to be equal, E according to P twiddle of F17, and if E according to P2 of F17 is also equal what it should be equal, E P twiddle of F17, then any linear combination of P1 and P2, because expectations are linear, any linear combination of P1 and P2 would also, under that linear combination of P, F17 would also have the same expectation. So this space is convex. This space is also convex. Is it true? No. I search in this space. The likelihood is convex. It doesn't mean that the space is convex. What does that mean for the space to be convex? Yeah, it is Rn. It is mappable to Rn. So yes, it is convex in the sense that if you take any two members, represent them by points in n-dimensional space that correspond to particular lambda values, any point along that line corresponds to other lambda values, so it's trivially convex. It's also convex. So we have two convex sets. They are different sets. They intersect at exactly one point. And the point they intersected is the maximum likelihood point of the exponential family, and at the same time it's the maximum entropy point of this family. The algorithm that we described operates along this line. You start with some arbitrary lambda values and you modify them. And as you modify them, you increase the likelihood of the data under them, and you converge to this point. Questions? Yes.
So to conclude, for Maxent models, the exponential model in the classes of all the models in your Maxent setting, the exponential model is the minimum. Or sorry, is the maximum, is the one that maximizes
The entropy.
Yeah.
Yes, that's what I mean by saying this is the maximum entropy point. So along all the models here, if you calculate the entropy of each one of them, the entropy of this one, and the entropy of this one, and the entropy of this one, and so forth, you will find that this one has the highest entropy among this line. And if you calculate the likelihood of the data along this one, you will find that this one has the highest likelihood of the data. Sometimes this point goes by the name MLME. It's the maximum likelihood, maximum entropy point. It's the maximum likelihood of the exponential family, the maximum entropy of the family of constraints satisfying, those that satisfy the constraints. I first introduced the exponential family in the context of a conditional distribution, because until now we dealt mostly with conditional distributions. We were looking at all of language through the lens of a sentence, and we're looking at sentence by using the chain rule to break it into a set of conditional distributions, conditioning a word on the history that came before it. So everything up until now we discussed was of the general form P of W given H. If you're a mathematician, a machine learning person, statistician, this is fine. If you're a linguist, it's a bit awkward in that we don't tend to think, and I say linguist, but I really mean if you're a human being, namely, if you think about language the way we normally think about language, we don't think about it as what is the probability of this word given this particular context. Even when we think about probabilities or sentences that are more likely or less likely, we usually think of the sentence as a whole. So there are many aspects of a sentence that are not particular to a particular position in the sentence. For example, some sentences are long, some sentences are short. Sentences of 10 words might be more or less likely than sentences of 27 words. Sentences of 3 words might be more likely. So how does the length of a sentence figure into its likelihood? We would like our models to capture that, to capture global aspects of a sentence, such as its length. N-grams don't do that directly. They do it kind of indirectly, because if the beginning of sentence symbol is part of your history, and if it survived the n-gram cutoff, then it does affect things, but they don't do it very well. Here are some other examples. Suppose you believe that sentences without verbs are not likely. How do you capture that with an n-gram? Either you can't, or it's extremely difficult. N-grams are about a particular position in a particular context. What if you want to capture something more general about the sentence? You want to believe the n-gram in general about word by word, but you also want to look at the whole thing and say, there is no verb here. That's not likely. Or there are 3 verbs here. That's not likely. What about syntactic constraints? Suppose you have a language that has rich morphology involving gender and count, like masculine, feminine, and singular, plural, or case, or any one of the other fancy things that English doesn't seem to have. Sentences that the subject is masculine, I'm sorry, that the noun is masculine, but the adjective describing the noun is feminine, would be agrammatical. You would think an n-gram might catch it if they're next to each other, but if they're not next to each other, it will not catch it. If you want to say, the girls I saw yesterday were pretty, but the word for pretty varies by whether it's masculine or feminine, whether it's the boys I saw yesterday or the girls I saw yesterday. An n-gram will not catch it, but a native speaker of the language will say that doesn't make sense, that's wrong, right? So there are syntactic constraints, there are grammatical constraints, there are all sorts of constraints that don't fall naturally into the straitjacket of predicting one word in a particular position relative to its immediate history. To do that, you can use a whole sentence language model. So you can start thinking about the probability of a sentence not necessarily using the chain rule. So let's try to think in that mindset. We want to estimate the probability of a sentence as a unit, almost like an atomic unit, P of sentence. In the past, we represented it as a long sequence of words, and then we used the chain rule, and then chop, 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 chop. But before we chop, 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 let's look at the whole sentence and try to estimate it. If we use the straightforward, sort of simple-minded view of estimate of count of the sentence over number of sentences, that's bad, because it's highly sparse, right? We know that's really bad. So let's not do that. But let's try to capture aspects of the sentences we care about with features. So one feature, call it feature f length of the sentence, would be number of words in the sentence. Or you can call it basically size of s, size of the sentence. Remember, features do not have to be binary. Another feature might be number of verbs. Just count the verbs. If there are particular linguistic constraints that you're concerned about, you can design a feature for any one of these constraints. If you want to make sure that gender matches gender, or plural and singular, whatever, there are many ways you can do that. It's not an automatic process, but you can imagine coming up with a set of functions that tries to capture that in the following sense. Suppose there's a particular kind of grammatical violation that you're concerned about, that your existing model doesn't deal well with. And suppose that because it's grammatically incorrect, it is very rare in real data. It occurs in only 2% of sentences. So if you create a specific violation feature, call it SV, specific violation feature, of the sentence, and you simply calculate whether for any given sentence the violation is present or not, and define the feature as 1 if the violation is present, and 0 otherwise. You can then calculate the expected value of this feature in your training data. Expected value in your training data, in p-twiddle, of the feature, specific violation, we said was 0.02. We said only 2% of sentences have that. You count. You evaluate this feature on every one of your sentences in your training data, evaluate whether it's 1 or 0, divide by the number of sentences, and you have your target. This is your target. Now that you have this feature, you throw it into a big model of lots of features, and you require that the final probability that you get from the process satisfies this constraint, namely the expectation of that feature according to that model matches 0.02. Well, suppose you had already an existing black box model that somebody gave you. Call it P sub 0 of the sentence. If you trusted P sub 0 and didn't want to modify it, you could use it to calculate the expectation of that violation. You do it by summing over all sentences the probability that your model assigned the sentence times that specific feature value of the sentence. And you might decide that it happens way too often. 30% of the probability mass, according to your probability, is sentences that have this violation. Your target is much lower. So you throw that feature in as the single feature in addition to P sub 0. So your model becomes P of S equals some normalizing constant times P of 0 of S, that's your initial baseline, times e to the lambda fs times f of, specific feature, specific violation, and f specific violation. This is not a summation, this is a single bump factor, a single feature. What do you think, and you train it using our method of iterative scaling. What lambda value do you think you will get? Positive, negative, large, small?
Depends on the usefulness of the feature.
Well, I gave you all the information you need. Your initial model assigns 30% of the probability mass to sentences that have the specific violation. But in the real world, in your real data, you discover that that particular violation occurs only 2% of the time. So I expect it'll be negative. I expected this bumping factor would bump it down such that every sentence in which the violation is present, and therefore f of SV of this is 1, and therefore this is e to the lambda, e to the lambda should bring it down. So it would be less than 1, namely lambda should be negative, and quite a large value negative because this is a big variation, whereas sentences that don't have the violation will not have this part. It would seem to you like you're not changing the value, but you're actually changing the value because the normalizing constant would be different. So you've created a bump over the model. You've created a distinction between sentences that violate and sentences that don't violate. And that distinction is as large as it needs to be to push the total mass of those that don't violate down to where it needs to be. If you remember the picture I gave you before, the map of the different space and the probabilities come out, imagine the P0, this is the space of all S's, and P0 is some complicated mountains and valleys here, some complicated area such that the total area sums to 1. If I now take the subset where the specific violation happens, what this bumping factor would do to P0 is it would take this space and push it down, and take this space and push it up. To where? To the point where the total volume under this is 0.02. So it's a way of taking whatever your existing model is and modifying it minimally to comply with whatever constraints you're throwing at it, whatever new information you're throwing at it. You can also start, instead of starting from P sub 0, you can start from scratch, from the uniform distribution. So let's do that and just see what the whole sentence exponential model look like. Whole sentence exponential model, also known as whole sentence maximum entropy model. The model is 1 over z e to the power of some lambda I fi of s. I goes from 1 to n. This is the entire model. What does it mean? It means that if you have two sentences that happen to produce the same values for the same feature, so two sentences that for any I, fi of the first sentence is the same as fi of the second sentence. In other words, the sentences appear to be the same to the features, to all the features. No feature distinguishes between them. If that's the case, the two sentences will get the same probability. Right? Because there's nothing else. The only way this model relies on the sentences to produce its value is by plugging it into the feature functions. If you have sentence 1, sentence 2 that have the same values here, you'll get the same result. Another way of saying it is that the model sees the sentences through their features and through their features alone. So you can call this a bag of features model. You are familiar with the term bag of words model. A bag of words model is a model where you assign probabilities based only on which words occurred in the document rather than their order. But it's a special case of a bag of features model, because features does not mean that you necessarily ignore order. It depends on what the features are. The features could include bigrams, in which case it's not a bag of words model. It could include trigrams, it could include long distance relationship, A triggering B but not B triggering A. Order can be very present. However, what it says is that once you define the features, you are done with considering what's going on in the data. That is the critical part of the modeling, is choosing the features. Once you chose them, the rest is automatic. The nice thing is that you can choose any features you want. Can choose any feature. And I left space here. What is the requirement?
It should not be very sparse.
That's true. That's not the one I had in mind, but yes, it's true. If the feature is extremely sparse, then pinning them to their value may be a little more than you want to do, more too demanding, too over-specific. But there's another more fundamental thing, is that the features have to be computable. For example, I think I gave you a similar example before, but now we put it in the context of this whole sentence model. Suppose you notice that 20% of sentences in a particular corpus are funny. You could define feature funny and give it 1 if it's funny and 0 otherwise. You can even make it a continuous valued feature, how funny it is. But how are you going to compute that? We don't know how to compute funniness. You may have noticed 20% of them funny by making a personal judgment reading them. But other people may disagree. Even if other people agree, if we don't have a way of computing it, we can't plug it in. You can approximate funniness. Suppose you came up with an artificial intelligence algorithm that takes as input a sentence and produces as output whether it's funny or not. And suppose that algorithm, being an AI algorithm, is not always right. It may still be a useful feature. The feature would not be, is the sentence funny? The feature would be, was the sentence classified as funny by this algorithm version 3.4? You know, a particular version of the algorithm, namely a particular function, computable function, that produces a number. As long as that number is somewhat related to your notion of funniness, it may do you some good. Because suppose your underlying model that you start with is very good in every aspect except it underestimates the prevalence of funny sentences. By putting in your approximation to the property of funniness and training on it, it will get a positive bump factor, a positive lambda. And it would tend to bump up the probability of sentences that it considers funny. Now, true, some sentences that the algorithm, the AI algorithm, fails to recognize as funny will not be bumped up. But many will. And others will be bumped down appropriately. So if you have in mind a particular linguistic property that you think is not captured by your model, even if you cannot capture it completely accurately with your AI algorithm, as long as you can capture it to some extent, it's more than random, you can put it in, it should do you some good. If it's completely random, you can put it in and it will not do you any harm. I gave the example of funny, but think of things that are more bread and butter linguistic. Parsable. Is the sentence parsable? Is it syntactically correct? Well, depending on your assumptions, we don't have parsers that are completely accurate on that, right? But we have parsers that are pretty darn good. That would tell you whether a sentence is, syntactically correct by some linguistic theory. And if you just use that feature, parsable by Joe's parser version 1.2, namely one particular well-defined computation, capture it in a function, show that there's discrepancy between the prevalence of that feature or the expectation of that feature in the real data versus the cumulative mass that your current model assigns to such sentences, then throwing in that feature will end up getting a meaningful lambda value, and it will improve your model.
Is there any reason why you could only apply this model to sentences and not linguistic structures which are longer, such as whole paragraphs?
No, you can absolutely apply it to documents as well. But let's talk about the practicalities of using this model. We'll talk about it in the context of sentences, but it applies even more to documents and other structures. Remember that we needed to calculate the normalizing factor when we did conditional models. The normalizing factor for the conditional models was z of h, was a function of h. And to calculate it, we had to sum over all the words in the vocabulary, right? And we summed over the part of the model that was not normalized. We sum over this part. E to the sum lambda I fi. Fi here was h and w. That was our definition of a normalizing constant. And I mentioned to you that this is not trivial computation because you have to do a loop over the vocabulary, which is on the order of 100,000. And for each one of these, you need to add together whatever features are active here out of n possible features, and multiply them together and add everything together. And there's a bit of computation. If you have to do it a lot, that is a significant computational bottleneck. It's doable, but barely so. It always stretches the limit of our computational ability. What do you need to do here to calculate z? What is the definition of z here? The best way to see it is to say the history is null. There's no history. Z is defined as a sum of just this part, e to the sigma lambda I fi of s, sum over what? I'm sorry? There's no history.
Sentence in your training data?
Nope. This was not the words in your training data. This was the words in your vocabulary. This is a summation over types. All possible sentences in the universe. So there's a little practical problem here. This is also called the partition function. It comes from statistical mechanics or thermodynamics, where this is called the Boltzmann distribution, and it's a very fundamental part of statistical mechanics. And the summation there is also over an equally hopeless space. And there's a lot of work on how to estimate it. Yep.
We do a similar trick that we did with backset modeling, where instead of summing over all possible sentences, we sum over all sentences in our data and then take an average and then divide that by the number of sentences we have.
We can't. The reason we can't is what we did with maxent, we did when we wanted to estimate the expectation under the empirical distribution. Here we're not talking about the empirical distribution. We're talking about our current distribution, just normalizing it. We can't do that. We do have two solutions. One of them to argue that we don't need z many times. And the other one is to try to estimate z anyway. So I'll go over both of them. First of all, the argument why we actually don't need z. The model needs to be trained and it needs to be used. Let me first show you that to be used, we don't need z. We don't need the normalizing constant. It depends, of course, what you use it for. So typical usage of this model is, say, interface to a speech recognizer. And a speech recognizer, you say a sentence into it, and it's supposed to produce an output. And you're effectively searching the space of all possible sentences, although you're doing it with some cutoffs and with clever filtering of the space so that, I don't know how much you know about speech recognition, but you're basically doing a search, a heuristic search in the space of all sentences. And in the end, you have, let's say, the 1,000 top sentences, most likely sentences. And you might want to consider not only the degree of acoustic match, but also how likely they are linguistically. That's where the language model comes in. But if you're comparing, if all you care about is the comparison of the likelihood of all your candidate sentences, z is common to all of them. It's right here. So you only care about the ratio between the likelihood of one candidate and the likelihood of another candidate. You don't care about the absolute value. I don't care about the sentence being exactly 10 to the negative 38 likely, which is the kind of likelihood we're talking about. I only care about which one is more than the other and by how much. So I don't need z, I don't need a normalizing constant for using the model, at least for speech recognition. And you can make similar arguments in machine translation and other areas. You can go back to, if you go back to the Bayes, remember our source channel thing? Whatever thing you have that you're maximizing, that you're choosing, is the argmax over all possible things. Thing being the output of the decoder or the new language or whatever it is that comes out of the posterior of that thing given the evidence, given the data. And since you're only taking the max, you don't care, z would just be a common constant to all of them. Okay? So we don't need that. Now for training the model, okay, so we don't need to know z for using the model. This is not true, by the way, if we use the conditional model of P of word given history, because different candidate sentences would have different histories along the way. And these histories would not be the same, so we would need to know what it is. So in some sense, we made the problem worse by making the normalizing constant impossible to compute, but at the same time, we also make it not needed in many situations. For training the model, remember that to train it, we go through a process of new lambda of iteration L plus 1, I, equals the old lambda, iteration L, plus the log of the ratio between the expected value in our training data of Fi and the expected ratio of our current model, based on current model. The top here is fixed. It's just the empirical prevalence of the feature in the data. The bottom is not, and I forget why I don't need it. Ah. So imagine the features being binary. I can find, so I really care about this one, finding this one. The expected, sorry, this is P sub lambda L. So this is the expectation according to our model of iteration L of a particular Fi. Assume for simplicity that the Fi's are binary. I can find the expectation according to our model, let's say according to lambda, of Fi by looking at the ratio of the probability according to our model that probability according to our model that Fi of S is 1 by the probability according to our model that Fi of S is 0. If I know this ratio, I know the expected value of Fi. Is that clear why? Let's say this ratio, for example, was 2 to 1. Then the expected value of the feature was 2/3. Hello? Does it make sense? Okay. So knowing this ratio is enough. But this ratio, again, cancels out z. Because z occurs here and z occurs here. So I don't need to know z for using the model or nor for training the model. Malcolm, you had a question?
Yeah, so in the third board on when we wrote the ratio, to me that looks like those the exact same terms. It's like P lambda and FIS. So, okay. So the event of the
Sorry, the probability, according to our current model, that the sentence would be assigned by this feature 1 versus the probability according to our model that the sentence would be assigned by the same feature 0. If it's a binary feature, the sum of these two must be 1, right? And the same argument actually applies when there are more than 2 values for the feature. You basically don't need to normalize it because you just need to know the ratio of the probability mass that's assigned to each value. And you know that they all sum to 1.
What if the feature outputs a real value? That's not a binary feature.
Well, if I could write down the form of that probability that a feature of S is some particular value x, if I could write it explicitly, then I could normalize it. But in practice, I will bucketize it because I still don't know what this is. I still need to show you how to estimate what this is. All I was arguing was that if I could estimate something like this and something like that, then I don't need the explicit value of z to do the update rule. So I can go about training the model without ever knowing the value of z. This kind of approach falls into a area in statistics called pseudo-likelihood. Really what we're working with is only this part. It's not normalized. And if it's not normalized, it's not a real likelihood. But we don't need to normalize it. We can work with it because for all our needs, both for training the model and for using it, it's not needed. A real pseudo-likelihood is even harder. Sometimes it's not even normalizable. This is normalizable. We just computationally hard to compute Z. But sometimes you have a score of some sort that it behaves like a likelihood, but it's not normalizable. It's called a pseudo-likelihood.
But we still have to compute Z of H for the when we're taking into account the histories, right?
If you choose the model of the sentence using the chain rule as a product of conditional probabilities, then we are in this world where Z of H does need to be calculated, but it can be calculated with a loop of size V. If you choose the model of the world without using the chain rule, just a bag of features of the whole sentence, then there's no Z of H, there's just Z, and it cannot be calculated, but we don't need it.
In the case when you don't have a normalized probability, could you simply take a set of feature function, a weighted set of feature functions and train on data with whatever training method you want and use that to estimate not exactly the probability but the comparative likelihood of two sentences or whatever you want?
Yes, and in fact you don't even do maximum likelihood training. You can do SVM, you can do maximum discriminative training, yes. In fact, since you brought it up, let me mention that. One way of looking at these exponential models is to look at their log probabilities. If the model is P of S equals 1 over Z e to the power of some delta I Fi, then the log probability of the sentence is negative log Z, which is some constant, plus sum of I Fi of S. You can think of the log probability as a score function. It's just a score, such that a better sentence gets a higher score. Okay? If it's just a score, if all sentences get this component, which is a constant, we don't care about it. Cross it out. What you get here is a linear combination of scores by different features. So you have F features or F graders, and they each give a score. If they're binary features, they give a score of 0 or 1. But they could be very complicated features, and they can give score on a continuous range or what have you. The lambdas are the weights you assign to scores. So this becomes a linear scoring competition, right? You can ignore or forget for a moment the probabilistic interpretation of it. And you can just ask yourself what values of the lambdas, namely what linear combination of the scores, would give him the best discrimination power, or the lowest error rate, or SVM, or whatever you want. So this is a direct relationship. Every exponential model can be viewed as a linear separator based on log probability. But of course not the other way around. You can now throw in all sorts of, I guess the other way around too, if you throw in just features, but you can now imagine higher order features that will correspond to a more complex model. Let me go back to the whole sentence model, because there's one remaining problem to be solved to be able to train it. I said this is the heart of the training algorithm. This is easy This is just the empirical frequency of the feature in the training data. This is what I need to do, and all I argued is that I don't need z. I can ignore the z part. But I still need to solve this somehow. So how do I solve this? This is the expectation according to my current model of a particular feature. So we want to calculate the expectation according to my current model, some given model, of a particular feature, fi, so I won't even write the I, of some feature of a sentence. Except I don't need the z. So I would write it as sum over all sentences of my model, the probability my model assigns to the sentence, times the feature value of the sentence. I will write it explicitly as sum 1 over z e to the sum lambda I fi of s times this is fi of s, this is f of s. So this R indexed I, because I goes from 1 to n here. But this f is one of those f's. It's the one from here. Now I said that I don't need the z, because it'll fall out anyway. So I can pretend that I have it, and then later it'll fall out. But I still need to calculate this. And this is summation over all sentences in the world. All sentences in the known universe. Okay? So I need to somehow go over all the sentences in the universe, of which there are a gazillion to the power of gazillion, calculate this value, multiply them together and add them together. How am I going to do that? I'll give you a hint. I'm not going to calculate it exactly, I'm going to estimate it. How do you estimate the expected value of some quantity from a very, very large population? Sample. I'm going to sample. I'm going to sample sentences. And here's the idea. If I can sample sentences according to this distribution, and then count the relative frequency of that in that sample of the times when the feature is on, this will give me an estimate of the true expectation under this distribution. And it's true also for non-binary features, namely if the feature here could have any value under some conditions. One way to estimate the expectation of this feature under this distribution is to look at the actual empirical or the sample expectation of this feature in a sample that was drawn from this distribution. Let me spell it out more exactly. The expectation according to some distribution P of some feature f is approximated by the sample average of the value of the feature, where S is drawn from P. Ponder this for a little bit. Suppose I want to know the expected height of a person in the United States. No, not a good example, because I need different probabilities for different people. What's a good example? Suppose I want to know the expected probability that if I pick up a dollar at random from all the dollars circulating in America, it will be a dollar that belongs to a conservative person versus to a Republican versus to a Democrat, assuming everybody is either a Democrat or Republican. Okay? Now, I have to draw the dollars. I have to sum over all the dollars in America. There are way too many. Some of the dollars belong to Bill Gates. I don't know whether he's a Republican or not. Actually, I do know, I think. Some of them belong to poor people. Some of them belong to rich people. Some people are, is this the example I want to give? Let me think.
So are you comparing sentences to people or dollars?
That's what I'm not sure. Sentences to dollars. Nah.
Features the political affiliation.
Yeah, all right, let me think through it first.
Yeah.
Try to convince yourself on your own that this is right, and then I'll come up with an example. Do you have a suggestion?
Do you place any sort of restriction on the sentences, the set of sentences? I mean, you can have infinitely long sentences technically.
Right,
So
you could. You could either make sure that it's just a bona fide distribution so that the tails converge, or you can just decide a priori no more than 1,000 words in a sentence. Not a real problem. All right, I need to come up with an example.
So thinking about if you pick a random dollar, what's the probability of any person owning it?
Is that what I want? What is the feature? I want a feature that is 1 if you're a Democrat and 0 if you're not. Okay? The expected,
Say 1 if you're rich and 0 if you're poor.
that's fine too.
Yeah. Then the sentences will be the people. So you will be assigning each person a probability.
Right, but that's where my problem is. I want different people to have different probabilities.
Yeah, so different people will have different features, like if they are rich, if they are students, if they are male or female, these are features.
Okay, but I'm trying to estimate here the probability, the expectation of a particular feature.
Oh, okay.
I'm not even trying to solve a exponential model here. There's nothing exponential model here. This is a particular feature.
Okay,
And
yeah, and then you have, like, the feature is whether this person is a Democrat. And basically you want to estimate the expectation of a person being a Democrat in the whole population, or the proportion of Democrats in the whole population. And
All right.
sample people to do that.
Going back to your dollar example, you need
Uh-huh.
some variation among the bills. Like you're perhaps estimating the probability of a word being a particular type of word. So you would want to have like dollar bills, $5 bills, $10 bills, and so on. And then the feature might be does it belong to a Democrat or a Republican, and you're predicting whether it's a dollar bill or a $5 bill.
All right, maybe that would work. Give me a minute to think about it. I think I can come up with a maybe even simpler.
I have another example.
Okay.
So let's think about a raffle.
Okay.
So different people put different number of tickets in the box.
Okay.
So
Good.
there's a probability distribution over people, and the feature is whether they are Democrat.
Okay. All right. Yeah, this is. I think all of your suggestions are doable, but let's go with this one. I like it. All right, people have different wealth. I mean, this is really what I was driving at with wealth. They can buy more lottery tickets. And they bought lottery tickets, and they mark all the lottery tickets with their political conviction, whether they're liberal or conservative. So it's L or C, okay? And they put it into the box, and we're basically trying to see what is the expectation of being a liberal, of the ticket being a liberal ticket, okay? I can do it by summing over all people and looking at the, well, I actually have to sum over all tickets. No, it's over all people.
Summing is drawing a ticket, right?
Right.
To find the expectation, you want to sum that over.
Right, okay. So here it would be summing over all people, and nope. Because what might my feature there be?
Yeah, the feature is whether they are different.
Yes, Malcolm.
So why is there so much difficulty in just taking, why couldn't you just draw your sample of tickets and then compute the feature value on each ticket and then
Yes, that's the
an average of
point.
that? Why couldn't you just do?
Well, the difference, I have to admit I'm confused by the example. Let me go back in my free time and think of an example and put it on Piazza. But let's talk about this specifically, not any particular example. The difference between these two is that this, exactly computing this, is a summation over all sentences of P sentence times F sentence. Doing this exactly means summation over all possible sentences, and it's a huge space. This is a sample that you're free to choose the size of. The larger the sample, the more accurate your estimate would be. And the trick here is that sometimes distributions can be sampled from, but cannot be summed over. Sometimes I can sample in a way that I can show is proportionately to the distribution, such that rich people are more likely to be chosen than poor people. But I don't have to explicitly sum over all the people, because there are 300 million of them or 7 billion of them. So this is computationally difficult. This is computationally variable, depending on how big your sample is. How big your sample needs to be depends to some extent on what range of values the features can take. If the feature is binary, it's quite simple. You know, there's a theory of sampling that says if you're looking for a binary 0 or 1 thing and you want to estimate its probability, it's like how many flips of a coin do you need to have the right confidence interval around it. If the features have a larger distribution, there's also theory, it's a more complicated theory of how many samples you need. The one thing you need to worry about is what if the features have an unbounded range. A feature can have very small value, but also very extreme large value. And then if your sample is not large enough, you may not hit that extreme value, and that will skew your sample average. So the example here is, if you're trying to estimate the average wealth of Americans, you can sample 1,000 Americans. It's a pretty good estimate, except there's a Bill Gates. And you may not hit Bill Gates in your sample of 1,000, and that would significantly skew down your sample average relative to the true average. Whereas if by chance you hit Gates, it will skew it up by a lot. So because the wealth distribution in the United States is so extreme, your sample average would not be as reliable an estimate of the true average as it would be if it was not so extreme. So it's the extreme, rare extreme values that complicate things. In the case of binary features, which is what we use most of the time, or features that take on the values 0, 1, 2, 3, 4, 5, it's not a problem. The range is very narrow. You don't need a large sample.
Could you smooth over your sample?
What do you mean by that? So you estimate based
You
on...
know the bounds of your feature and
Right.
the values it can take, but
Right.
your sample doesn't happen to hit those. Could you smooth to account for those?
Or maybe more generally, you can estimate the true sample mean by taking the true population mean by taking your sample mean and shrink it or smooth it with some other estimate. Sure. But anyway, our solution is to sample from the distribution. And the distribution we sample from is this one. Except remember, we don't need to know Z. So we ignore it. And the question is, how do you sample from an exponential distribution like that? So you know the lambdas because of the lambdas of the current iteration. How do you generate an item that was sampled from this distribution? Turns out it's non-trivial. In fact, it is probably intractable to do it exactly. And I say intractable, exponential. I mean, you can. So how does one sample from an exponential distribution? Ooh, I need to let you go. Let me write a sentence. From a given exponential probability function. So you're given an exponential probability distribution, either with a 0 or without it, it doesn't matter. How do you generate sentences randomly that have the property that the probability of being generated is directly proportional to this expression? It is computationally very difficult, and you approximate it again using random walk, effectively. So we'll talk about it next time. Oh, next time we have an exam. We won't talk about it next time. We'll talk about it time after that. Questions? We talked about the exam already.
If you want, we can talk about it next time.
I'm sure we will. All right, thank you.